Hey, Science 30s, and today we're going to be discussing topic 1.4 of the acid deposition chapter, quantifying acid deposition and monitoring its effects. To start off with, I'm going to get you to take a look at this video about buffering and buffering capacity, just to refresh your memory about the concept, because both of these concepts are going to play a heavy role in today's conversation. I want to start off today's lesson with just a discussion about the two types of data that we can use to describe an acid. We have which is called qualitative data, and something that's called quantitative data. Qualitative data, we've discussed this already before. This would be like with pH indicators. We have a color change that's indicating the change of a pH of a substance, so that would be called qualitative data. Quantitative data is anything that we use to basically represent a number, to represent the strength of an acid. In this case, we're dealing with pH values, concentration of hydronium, which we've talked about as well in a previous topic when we were discussing how to calculate pH and hydronium concentrations from one another. So today's discussion on titrations is a beautiful marrying of these two types of data. We're going to use a titration setup like this one to basically calculate the concentration of an unknown acid. Now, before I go on with this, I want to make one thing clear. Titrations can be used to calculate both an unknown acid's concentration or the concentration of an unknown base. My entire discussion today is going to be predicated on an acid, an unknown acid that we're going to determine the concentration of. But be aware that everything I discuss related to the acid, if I had an unknown base, everything I'd be discussing about the solution that we didn't know the concentration of and the solution that we do know the concentration of, we would just flip them. So in this case, we've got a sample that's unknown, that's an acid, and then we add a substance to it called a titrant. But if it was an unknown base, the titrant would not be a base anymore. The titrant would be an acid. But for my discussions and to save time, we're only going to refer to this setup in the case of an acid that's a sample. But be aware, we could also calculate the concentration of an unknown base by using a known acid. But in this case, we're going to show you how to calculate the concentration of an unknown acid. Okay, so what is a titration? Well, a titration, the setup is right here, and there are several pages in your notes related to it. I'm going to basically bring you up to here because the diagram is on this page of the notes. But essentially what we're going to do is we're going to take an unknown acid that we don't know the concentration of. That's going to be called the sample. The sample is going to be put into an Erlenmeyer flask, which is below, set up in a kind of a C-stand with a clamp on it that's going to be holding a burette, which is a long piece of glass that has a little latch on it, which is called the stopcock, which allows me to quickly release solutions that are in the burette, and it can be added at a very slow rate into the sample. Now, in this case, it's an unknown acid that's the sample, so we're going to actually undergo an acid-base reaction with it to calculate its concentration. We are going to add an amount of a base, in this case, that we do know the concentration of. So that known solution is called the titrant. So in this case, the titrant, or the standard solution, is going to be added into the sample. And we're going to calculate how much of the titrant is needed to actually react fully with the sample. So in this case, how much of the base is needed to react fully with the acid that's in the sample. A couple of things about how we get it in there. The standard solution would be in a beaker. We would then use a pipette with a bulb to basically, pull up the standard solution into the pipette, making sure that we don't go past the bulb and get anything into the actual bulb, because remember, these are acids and bases, they're corrosive. We don't want to dissolve the rubber of the pipette bulb. Remember, the glass will be non-reactive with an acid and a base. So we basically take this solution, the standard solution from the pipette, and then drop it into the burette with the stopcock closed, and then we're ready to basically start adding that standard solution to the titrant. Now, to do that, before we do this, we're going to also add to the sample a pH indicator. So, for example, something like bromothiamyl blue or phenethylamine, we're going to add one of those pH indicators that we discussed earlier in the chapter that has a specific color, and then we'll change to another color once an acid or once a pH value has changed. So that indicator is going to change color when the titrant has fully reacted with the sample, and that will indicate to us what's called the end point of the reaction. At what point, and remember, in an acid-base reaction, it all boils down to two ions. It's going to be the hydroxide in the titrant in this case that's going to react with the hydronium in the sample. Once all my hydronium in the sample has been used up, that's the end point of the reaction, and then this sample no longer has a buffering capacity against the increase of the base that's being added. And eventually then, once all the hydronium is added, then the pH of the sample will spike in an upward direction because it's a base that we're adding to it, and that's going to cause a color change in the pH indicator. So that's sort of what the process is. And then we're going to run this a few times. We're going to do about 3 or 4 runs of this experiment to try to get accurate values on how much of the titrant is being added to the sample. And by the way, the sample, every time we do this experiment, the sample is going to have a standard volume. We're not changing the volume of the sample. So, for example, we could say the sample is always going to be a 10 mil value, and then we've got to figure out how much of the titrant is going to be required to neutralize that 10 mil sample of the unknown solution. Okay, so when this is all said and done, I will kind of give you an example here in a couple seconds of the values you get. So let's say, we'll go to that in a couple seconds. But when this is all said and done, we're going to use well, before I actually discuss that, quickly take a look at this video really quickly right here. Sorry, look at what a titration experiment looks like in an actual animated version. Like they show you what the titration looks like, just so you can visualize sort of what's happening in the titration. And then I'll get back to you discussing what the formula is that we're going to use with that reaction or with that process. Okay, so once you've done your titrations and you figure out how much of the titrant is needed to react with the sample, you now have everything you need to calculate the value of the concentration of that sample. And we do that by using a formula known as the concentration formula, which is concentration, which is in the units, moles over liters, is going to be equal to the number of moles of a substance divided by the volume. Well, pretty much everyone here can tell me what concentration is. It's how concentrated a substance is in water, how many particles are found in each unit of that solution, and everyone knows what volume is. And by the way, the volume always, in this case, has to always be in liters. Some of you may not know what moles are. If you've taken chemistry, you understand what a mole is, but if you're not a chemistry person here in my class, what is a mole? Well, a mole is a measure of unit in chemistry that was devised by an Italian scientist by the name of Amedeo Avogadro, it's called Avogadro's number. And Avogadro's number is 10 times 10 to the 23rd, a really large number, which refers to the number of atoms or molecules or ions that are found in a substance. Now, the best way to think about this is, what's a mole? I don't get it. Well, go into a grocery store, you buy a dozen eggs. A dozen eggs, you know what a dozen eggs are? It's 12. We don't have to think about what a dozen eggs is. Well, in chemistry, we just use the term moles. It's a very large number to represent something in chemistry that we can't really see. So it's always a standard amount of atoms or molecules or ions that are found in a substance. And in this case, the moles are going to be sort of the linchpin in the operation. Because in a reaction like this, where we have an acid-base reaction, hydroxide reacting with hydronium, that reaction is always occurring in a 1-to-1 ratio. One hydroxide reacts with one hydronium, they form 2 molecules of water. That reaction is 1-to-1. So if I know the number of moles of one, let's say I know the number of moles of my hydroxide, I automatically know the number of moles of my hydronium because they will be the same. And that's a very important thing to remember in this equation, is that if you can calculate the moles of one of the two substances, you automatically know the number of moles in both of the substances. And then from that information, you can then calculate an unknown concentration. Let me explain how that works using an example. Here's an example in your notes. It's up there. You see the results of a titration that's been done. You've got a solution of 1.50 moles per liter sodium hydroxide. That's the titrant. It's going to be titrated into exactly 10 mils of an unknown concentration of hydrochloric acid. Determine the concentration of the acid. Okay, perfect. So the first thing I want to do is I know that I've got my concentration of my sodium hydroxide. I'm going to basically use this. I'm going to plug this into my concentration formula. I've got concentration equals N over V. I know my concentration, and because I've done the titration experiment, I now also know the volume of the titrant that was required to completely react with the acid. And you'll notice that there are 4 trials here. We're only going to use data from trials 2, 3, and 4 because in trial 1, you can see that the indicator that was used was methyl orange, which goes from red to yellow. In this case, we overshot on the first one. The endpoint was beyond, we went past the endpoint. So we didn't actually, when we do the titration, what we're looking for is as we add the titrant to the sample, you want the color change to be in between the 2 colors. So in the case of methyl orange, it's between red and yellow. So you want to stop adding the titrant when you hit a solid orange. If you've hit the yellow, you've gone too far. So in this case, the first sample, we're going to throw that one away. We overshot that one by a little bit. But the third and second and fourth trials, we have about 12.7 mils, 12.8 mils, 12.8 mils. That's consistent values. So I'm going to take those 3 volumes in milliliters, divide by 3. It's going to give me roughly still 12.8 milliliters. But remember, this is a concentration formula. Volume has to be in liters. So I'm going to take my 12.8 milliliters, divide by 1,000. That's going to give me a value of 0.0128 milliliters. So now I know of my titrant, I know my volume, as well as I know my concentration. So from that information, if I plug it into my concentration formula, I can actually determine the number of moles of hydroxide that are in the base, which is going to be, in this case, 0.00192 moles of hydroxide. So now that I know the moles of hydroxide, I automatically know the moles of what? I know the moles now of my hydronium in the unknown sample of hydrochloric acid. So this information now can be plugged into, initially I didn't know my number of moles of hydrochloric acid. All I knew was the volume that was in the sample in the Erlenmeyer flask, which was in this case 10 mils. So all I knew initially was I had 0.01 liters of hydrochloric acid, but I need 2 variables in that concentration equation to make it work. Well, this is my second variable, which is moles. So I now know that I can calculate my concentration of hydronium from the number of moles. And by the way, where is this number of moles coming from? This number of moles is equal to that number of moles right there. This number of moles becomes that number of moles that's unknown. So you can see that the trend here is I calculate the number of moles in my titrant, and when I discover that, I can then plug that mole value into the mole value for my sample, or my unknown concentration, in this case, of hydrochloric acid. At that point, I'm going to plug it into my equation. I'm going to get 0.00192 moles, which is my N value, divided by 0.01 liters, which is my volume value, or my V value. That's going to give me a concentration of that unknown hydrochloric acid of 0.192 moles per liter of hydronium. This, ladies and gentlemen, right down there, that's the answer to your question right there. That's how you do it. And then all the work is shown there. Plus, as you can see on these couple of slides that I basically have laid out for you, this information is all provided. Plus, there's a little bit of information here about the initial and final burette readings. Give that a read in your notes. That's a good thing to look at as well. And again, what the indicator color is doing. This is a great little slide that kind of wraps up some of the maybe more mysterious concepts of the titration. You can see here's all the work. Here's step 1 in the notes. And again, it's all there. You can take a look at that at your discretion. Take a look at the notes. It's all laid out very nicely in the notes. Please read through it. It's going to really help you out if this didn't really make maybe as much sense as it could have, because it is a little bit messy on the board. But everything I've given you is basically here. By the way, the equation for concentration equals N over V. You're going to find that equation on page 10 of your Science 30 data booklet. So that's where you're going to find that equation. And then again, final step here. Here's what I just gave you. So look at those 3 pages. Those are really important. Now, there is one other thing I want to discuss with you as well, and this is sort of in the notes. I don't have it up on the board. Because I now know my concentration of hydronium, I can automatically now calculate the pH of the acid. So if I take my equation that we learned in the earlier part of this unit, which is my negative log 10 of the concentration of hydronium equals pH, that means I'm going to have a negative log 10 value of 0.192 moles per liter, which is going to give me a pH value of roughly 0.717. So a pH of less than 1, very strong acid we're dealing with in this unknown sample. So this is so you can calculate pH based on the titration as well. It isn't just concentration you can calculate. You can also calculate the pH of the substance. Okay, now it's your turn. All right, you got a couple of examples here that are up on the slides. I'm going to take a look at this page of the notes. Got all your data here for you. There's nothing in the notes to indicate how to do this. I'm going to bring up the slide here really quickly just to tell you what the numbers are so that you can see if you're doing this right at home. And I'll give you a couple seconds, maybe pause me, but I'm about to flip the slide, so if you don't want to get a giveaway. Spoiler alert, answers coming up. Here we go. All right. So here is a very messy board. I apologize. But again, there's only so much I can do with a little small whiteboard like this. So we've got our first substance where we've got a titrate of potassium hydroxide is going to be added to a sample of sulfuric acid, H2SO4. Oh, sorry, pardon me. Cancel that. See, again, you got to read this very careful. Right now, we're going to flip this thing on its head. So far, we've been discussing a titration with an acid being titrated by a base. We're going to flip that now. In this case, we've got an unknown base as our sample. The acid now is going to be the titrate. So we flip the acid and the base, like I said in the earlier part of the lesson. You can flip it. So this is the other scenario. So now the base is in the Erlenmeyer flask. The acid is in the burette. We're going to we're going to hit the buffering capacity of the base by adding a sample of known sulfuric acid. So we figure out what the volume of my sulfuric acid is. There were 4 trials. I'm going to eliminate 12.1 because it's not the same as it's not close to the other 3. I've got 12.6, 12.5, 12.6. That's going to equal 12.6 milliliters. That gives me my volume to put in the equation. I know the concentration, which is 0.2 moles per liter. That's going to give me a number of moles for my sulfuric acid of 0.00252 moles, which can now be converted to moles on my unknown sample of potassium hydroxide. That mole value equals originally it was unknown, but now I know it because I know the number of moles in my base or my acid. My base moles now are going to be 0.00252 moles. I know that the volume that we were putting it into was 15 mils, so that's going to be 0.015. If I plug those 2 values into my equation, what I'm going to find is the answer for the first question right here, all squared off, nice and neat. The concentration of my base in this case is 0.168 moles per liter of potassium hydroxide. The second one, I've got a concentration of, I'm going to also calculate a base here as well. So this is a base being titrated with an acid. So the sample is the base, the titrate is the acid. I've got 12 mils of barium hydroxide being titrated with 0.225 moles per liter of acetic acid. So what do? I've got my trials of volume of my acetic acid. I've got 14.8, 14.9, 14.2 is out. It's not as accurate as the others. I removed that. And 14.7. That gives me a volume of 14.8 mils. Convert that to liters, it's 0.0148 liters. At that point, I can take that plus the concentration that I know of my titrant of my acid, which is 0.225 moles per liter. I put those into my equation right here and here, my moles and my concentration and my volume, calculates my moles of my titrant to be 0.00333 moles of hydronium, which means that now that value can be calculated into my moles of barium hydroxide, because remember, my moles of my base or my acid is going to be equal to the number of moles of my base in these reactions. So I'm going to have a mole value in my barium hydroxide now of 0.00333 moles. I know that the volume of my barium hydroxide is 0.012, which is 12 milliliters. That's in liters, so I have to convert that. And then I'm going to plug these 2 values into the equation, and that's going to give me a concentration of barium hydroxide of 0.28 moles per liter of barium hydroxide. And that shouldn't be hydronium, that should be concentration of hydroxide. All right? That is it. What a mouthful. Lots of calculations there. Now it's your turn to do some practicing, folks. I want you to complete the titration analysis worksheet that I'm going to send you a link to. It's also on the bottom of the description of this video. As well, do practice questions 42, 43, 44, 49, 50, and 51 on pages 211 to 217, and questions 4, 5, 6, 7, and 8 on page 221 in your Science 30 textbook. Whew! Felt like I ran a marathon that one, folks. Again, if you have to watch this video again, please watch it again. Pause it. Lots of information today. So hopefully that helped you out. If not, you can always ask me in class, and I'll try to clarify it as best I can for you in person. Until next time, guys, thanks a lot for joining us, and we will see you for our final topic of the acid deposition unit 1.5 next time.